Hi gang, in this video we're going to continue our discussion of thermodynamics. Specifically, we're going to be looking at the second law of thermodynamics and what it means, which involves, of course, the concept of entropy. So we'll introduce entropy, we'll provide a thermodynamic definition of entropy, and then we'll actually look at something called the Boltzmann definition of entropy. We'll look at a couple of examples, such as what are entropy changes that occur during an isothermal process, isothermal meaning constant temperature, and we'll look at how entropy changes when we heat things and also undergo phase transitions. Okay, so what is the second law of thermodynamics? Most of us associate, particularly at the introductory level when we're first introducing entropy, that we talk about entropy as being increasing in any kind of spontaneous process. So that's what we normally assume to be the second law of thermodynamics. The entropy of the universe will increase. For an isolated system, what this means is, and of course we know that S from your previous discussion represents entropy, and that means that the entropy change for a process must be greater than or equal to zero. So qualitatively, we refer to the second law of thermodynamics as the increasing entropy as we proceed, and then quantitatively we talk about this entropy S, and we represent it as delta S, meaning the change in entropy for a process must be greater than or equal to zero. At equilibrium, what this means is Y equal. Well, equilibrium is when delta S for an isolated system is equal to zero. And you notice I'm using the term isolated here. We indicated in an earlier video that we divide the universe into two components, the system and the surroundings. So if the system is isolated, then this is true. And we'll certainly see some exceptions to this for individual systems. But what's important here is the basic definition. The universe being an isolated system obviously means then the delta S for the universe is greater than or equal to zero, and that kind of wraps us back around to what we said earlier, and that is that the second law indicates that the entropy of the universe will be increasing. The equal sign again refers to the equilibrium of the universe. The universe is striving toward equilibrium, and we'll talk a little bit about that in a later video. Alright, so we've used this term entropy, represented by S, and what does it mean? Well, again, in your introduction to entropy, no doubt in your general chemistry course or otherwise, you associate entropy with a degree of disorder. So increasing entropy means increasing disorder. But of course there has to be a mathematical definition. We are, of course, physical chemists, right? So that means we need to have a mathematical definition for entropy. So this is the definition of entropy in differential terms. The ds, of course, represents the infinitesimal change, the differential change in entropy, as being equivalent to dq with the subscript reversible, ReV for reversible, divided by T. So you'll notice that entropy changes are related both to heat transfer and to the temperature, and that's actually fairly important. The reversible allows entropy to be a function of state, so we're specifying a specific path, and again, we defined reversible in an earlier video as something that's infinitesimally close to equilibrium and involves infinitesimal changes. And so again, that ensures that entropy will be a function of state, which is actually fairly important in our definitions and computations associated with it. Now, associated with that definition of entropy, we have something called the Clausius Inequality, which is written this way with the ds greater than or equal to dq over t. And this is just a reformulation of, in fact, the second law of thermodynamics. The dq system, you'll notice we have a subscript sys here rather than on the previous slide ReV for reversible, and that means that ds is greater than or equal to dq system over t. dq system refers to any process regardless of path. So the difference here is that this is specific. Inequality refers to any possible path, whereas the definition of entropy refers to a reversible path. And of course, if we do have a reversible path, we again note that ds is going to be equal to dq reversible over t. So that's actually the difference here between that. So if it's a reversible path, then the ds, the differential change in entropy, is dq over t. But if it's not a reversible path, then ds is going to be greater than dq for whatever that particular path might be divided by t. And again, this is just a reformulation of the second law. Okay, so that was the thermodynamic definition of entropy. The Boltzmann definition, which we discussed earlier, deals with probabilities. And again, we talked about Boltzmann distributions in an earlier video. In this circumstance, Boltzmann, taking a statistical approach to systems in the definition of entropy, came up with this equation where he defined S as being equal to K times the natural log of W, okay? And in fact, this is Boltzmann's tombstone, and he has it engraved on his tombstone, except you'll note that, of course, it's log log instead of ln for natural log, but it is, what we're talking about is natural log here. So what are we talking about here? Well, W represents the number of ways to achieve a particular state. So you can imagine a situation where we have, for example, gas molecules filling up a room. Okay. Well, if you were to look at all the different gas molecules in the room, there are lots of different ways that those molecules could fill up the room. So that would have a large value of W. So that's what we're talking about here, the number of ways that we can configure the system. In this case, we're talking about the particles in the system to achieve a particular state. And the larger number of ways we can do that, the greater the entropy. We can relate this to disorder. If you think about, say, your room, there are lots of different ways for you to mess up your room so it's in a disordered state, as opposed to ways that can be in an ordered state. So the disordered state, because there are many more ways to achieve that, has a larger entropy than the ordered state. Now, there are actually some philosophical discussions that we could bring into this at this point, but we won't. This will come perhaps at a later time in conversation. But nonetheless, we can use this equation for entropy and dealing with the number of different ways. The other thing to point out in this equation, of course, is that the K in this equation is the Boltzmann constant that we have used in other calculations at this point. So we've got this nice little equation that relates to entropy, to the number of different ways that we can achieve a particular state, and that can relate, of course, to disorder. All right, so this relates the second law to the probability. It's much more probable to have a disordered state, so the entropy is higher in that circumstance, as we mentioned. It also means that we have a situation where a decrease in entropy is highly improbable. However, it is not impossible if we look at this particular definition of entropy, because one could certainly imagine during certainly in an infinite lifetime, but in a very long time span, there could be a circumstance where all the molecules in that room I was speaking of earlier could somehow move to a corner of the room, which would be a much lower entropy state, and that could happen. And in an infinite universe, it would happen. But that's a very, very low entropy, and it is highly improbable. But again, let me say it's not impossible. All right, so let's look at some particular changes. So first of all, we'll talk about an isothermal change, which means there's no change in temperature. And so we want to evaluate the entropy change for a situation where the temperature does not change. And so in this circumstance here, of course, since we're starting out with a differential form, of our equations, to get a finite change, what we need to do is integrate. It's our favorite thing to do, right? So we're going to integrate here, and this actually reduces pretty quickly in a situation like this, because first of all, if you integrate just ds, we get delta s in this circumstance. So that's trivial. And then because the t is constant, we can pull that outside the integral, so we've got 1 over t integrating just dq, and that then reverses to our simple equation that delta S is just equal to Q, the heat transferred in the process, and again reversible, divided by T, the temperature. All right, now what about a heating process? How do we go about doing that? Well, if we're dealing with heating, then one thing that we will note, of course, is that first of all, we note that our dq, going back to definitions of heat transfer in a temperature process involving temperature change, is just cdT. So in a circumstance like that, we replace the dq with cdT, and then we note that our temperature is not constant, so unlike the previous example, we can't pull that outside the integral. And so when we go about doing that, we're going to evaluate our integral, and in this case we're going to assume that the heat capacity is independent of temperature, that it's a constant. This won't always be the case, and we'll look at an example in a little bit where we have to take that into account. But if we do assume it's constant over the temperature range here, then we can pull that outside the integral, of course, and then we're left with c integrating dt over t, which you may recall from basic calculus that 1 over t dt, or 1 over x dx, is just equal to the natural log of x. And so that gives us an expression for delta S for our heating process as just being the heat capacity times the natural log of T2 over T1. T1 and T2 being the initial, and the T1 being the initial temperature, and T2 being the final temperature in this particular process. So we can actually use this equation whether it's heating or cooling, just involving a temperature change. And again, the assumption here is that the heat capacity is independent of temperature, and that's actually fairly important that we have made that assumption. So let's look at the situation where heat capacity is not independent of temperature, and here's one where we're talking about the heating of chloroform, and our heat capacity is given by this expression, where we note that it does depend on the temperature. It's a small temperature dependence, but it is a temperature dependence nonetheless. And so if we want to calculate the entropy change for that, we have to take that into account, which means we have to go back to integration. Now I'm going to run through this in a separate video on how to actually do the calculation, but here are the basic results. So here's the basic theory behind the situation and how we're going to set it up. Again, we're going to start with the situation where we have our basic definition for a process involving temperature change. We use a CP here, the subscript P, for a constant pressure process. And so there's our definition, and of course we need to integrate. Now the problem is when we integrate, we've got this situation where CP is given by this expression. So we have to make that substitution, and now we're integrating this. We can't just simply pull the heat capacity out of the integral. We have to include that in the integral because it does depend on temperature. All right. And so we've got to evaluate that integral in order to calculate delta S. So if we do this in the Wolfram Cloud browser notebook, this is what it might look like. And again, I'm going to create a separate video which actually runs through this. So the first thing is we're just entering our heat capacity. And what I've done here is I've used TP rather than T, just so that we're not confusing this with other variables, but that represents the temperature. I'm not using units here, and that's because, as I mentioned in the video, it will turn out in this circumstance that it's easier to avoid units, but you must make sure that all of your units are compatible, meaning that we need SI units, so that we've got joules per Kelvin per mole as the units for heat capacity, and that also means the temperatures have to be in kelvins, so we're going to have to add 273.15 to get the corresponding temperature in kelvins for our initial temperature and our final temperature. And then in Wolfram alpha, although this is a fairly trivial integral, using simple methods that you would have learned in calculus, but if we want to use the Wolfram product to do this, we just use the function integrate. We're integrating Cp over T, and this is the range over which we're integrating. And as I'll mention in the video, you could also use free-form Wolfram alpha methods to do this as well. And so we get an answer. So what are the units for our answer? The units for our answer, and again, if we're not using units, we need to be aware of this, but the units for entropy are joules per Kelvin per mole. And as long as we've got all of our numerical input in terms of SI units, we're good with that. So finally, let's talk about phase transitions. And so we're talking about entropy changes at, say, the melting point or boiling point of a substance. What we'll note is that when we're actually at the melting point or boiling point, we have an equilibrium. You may remember this, of course, from your initial exposure to phase transitions. And so because we're at an equilibrium situation, then it is a reversible process, and Q reversible is just going to be equal to delta H, the enthalpy change for that transition. Again, we're talking about a constant pressure process, so Q will be equal to delta H because it's constant pressure. And therefore, at the transition temperature, the equilibrium temperature, delta S, is just equal to delta H over T. It is important to note that this corresponds again to just the case when we're at the transition temperature. If we're at another temperature other than the transition temperature, then this equation doesn't work. And an example of this would be something like supercooled water. If we've cooled liquid water down to temperatures below 0 degrees Celsius, which is certainly possible under certain circumstances, the entropy change, to calculate the entropy change associated with the freezing of water at, say, -5 degrees Celsius, requires that we go through a reversal stepwise process in order to do that calculation. This is something we may talk a little bit more about at a later time. But right now we're just talking about at transition temperatures where we're at equilibrium, where it's reversible, and we have a constant temperature process. So it's fairly straightforward then to do the calculation. If we do this for liquids at their boiling point, then we find there's actually, for most liquids, that delta S for the transition from liquid to vapor at the boiling point is close to 85 joules per Kelvin per mole. If you do this calculation for a lot of liquids, you'll find it's actually very close to that. That's something called Trouton's rule. You'll notice that it's a positive entropy change, and that should make sense to you when you go from liquid to vapor. When you're going from liquid, which is in a more ordered state than the vapor, you would expect that the entropy change would be positive under those circumstances, and so that's what we indeed do see here in this circumstance. All right, but then there's water, which you know is always an exception. So let's calculate delta S for the boiling of water at 100 degrees Celsius, 373.15 Kelvin, where the enthalpy of vaporization is given here. If we do that calculation, we actually find that the value is much higher than what's predicted by Trouton's rule. It's 108, close to 109 joules per Kelvin per mole, and that's clearly significantly higher than what's predicted. So the question is, why is water higher? And I'm not going to answer that question here. It's something for you to think about, although I don't think you'll have to ponder this for a very long period of time. What is special about water that makes things so different? Why is the entropy change in going from the liquid to the vapor so much higher, which means there's a greater increase in disorder, if you will, relative to other liquids? So something to think about and I think you'll figure that one out pretty quickly. All right, so what about freezing of water? The same kind of idea. At 0 degrees Celsius, we need the enthalpy of fusion, which you'll notice is typically tabulated in positive values, but we're talking about freezing where we're going from the liquid to the solid, okay? And when we go from liquid to solid, we should be able to realize that it's going to be an exothermic process. So the enthalpies of fusion that are typically tabulated are positive, but you have to be aware of the appropriate sign for this. When you're going from solid to liquid, it's going to be endothermic, but if you're going from liquid to solid, it's going to be exothermic. So we just have to make sure when we do this that we have the negative sign in our equation. So we've got, here's our entropy of freezing, and we divide it by the freezing point temperature, which of course is 0 degrees Celsius, 273.15 kelvins, and do that calculation. So we get this negative 22 value. So the question is, why is it negative? All right, and what does this say about the process being spontaneous or not? If we're at 0 degrees Celsius, we do have an equilibrium process. So what's going on here? It's negative, of course, because we're going, and again, from the order-disorder relationship, we're going from less ordered to more ordered. Okay, so we're decreasing the entropy, hence the negative sign with regard to that. The other thing that we have to be aware of is that this is not an isolated system because heat is released into the surroundings. So if we want to calculate delta S for the universe, we need to include the surroundings. But you should be aware of the fact that because this is an equilibrium situation, delta S for the universe is going to be equal to what? What did we say earlier? For an equilibrium situation, delta S for the universe is going to be equal to 0. So that means that delta S for the surroundings in this circumstance would correspond to the positive, exactly the opposite, joules per Kelvin per mole. Now, an alternative question would be, what's delta S for the spontaneous freezing of supercooled water? And that's something that we'll address later on. So this concludes our discussion and our introduction of entropy and looking at some basic applications and changes. Future videos will go into this in more detail, and also look out for the future video which goes through the Wolfram calculation. In the meantime, have a great day.